The purpose of this video is to try and show how we derive, well, really what we're going to look, let me call it this. We want to determine the slope of the tangent line. We talked before how to find the slope of a straight line is very straightforward. You just choose 2 points on that line and you determine the rise over the run, or the vertical change over the horizontal change, and you have the slope. As a matter of fact, oftentimes, if you take your 2 points, a lot of times they'll call this point x1, y1, like this is point 1. And this point is x2, y2. Now this is based upon our typical xy axis. Now we know the slope, and this is also the slope equation that we use when we have 2 points on a line. But it also makes sense in terms of a curve, right? Because this distance, this vertical distance is y2 minus y1. So that's how far up we have to go. That's the rise. And then this distance is x2 minus x1, and that's the run. So it all fits together, rise over run. y2 minus y1 over x minus x1. All right. And this is your slope equation. Even if we're not given a graph, if we're just given 2 points, this is how we calculate the slope. Now let me do something that starts to get a little messy and a little complicated, but we need to understand this, because I'm going to redo what I did here, except instead of an x and y graph, I want to change it to function notation. Remember, function notation, y and f of x are interchangeable, but now I want to make my vertical axis f of x. Now function notation, let's remember, say you have a point x1, y1. Another way to write that is x1 f of x1. And that's because y1 I can rewrite as f of x1. So this is just the same concept. F of x and y are interchangeable. But since this is called y1, if I want to convert this to f of x, I need to call it f of x1. So I'm going to do the same thing over here. Here's my first point, x1, but I'm not going to write y1. I'm going to write f of x1. F of x1 is the same as y1, but I don't want to write y1 because I want my graph to be sort of like in function notation. So here's the second point, x2, y2, I'm not going to write y2, I'm going to write f of x2. These are really identical. All I'm doing is the first graph, it's x and y. In the second graph, it's instead of y, I'm replacing y with f of x. It's f versus f of x. Therefore, these points, instead of y1 and y2, I have f of x1 and f of x2. Therefore, with this notation, how could I calculate the slope? Well, in a sense, it's y2 minus y1, but of course it's not y anymore, so it would be f of x2 minus f of x1 over x2 minus x1. Once again, if you compare the two slope equations, all I've really done is replace the y's with f of x. All right, I do this because in a few minutes, I'm going to do this kind of thing on a graph, and if you're not aware of what I'm doing, then it could make it a bit confusing. So with that in place, let me go back to what I started talking about. We're going to try and find the slope of a tangent line. If you have a straight line, you find the slope, you choose 2 points on the line, you find the slope. The slope is the same for this whole line. We've talked about that before. No matter what point I'm at on my line, the slope is not going to change. However, what we're looking at now, we're not looking at straight lines. We're looking at lines that are curved. So what we talked about before is, if someone says, what's the slope of this line? You have to ask them, well, you need to tell me where you want to know the slope, because the slope of this line is constantly changing. So as soon as they choose a value of x, then you can go to your curve. And then what we do is, I'm going to even take a ruler. We try and draw what's called a tangent line. A tangent line is the line that sort of goes right next to the graph and intersects the graph at only one point, the point we care about, and then keeps going. So it's really a straight line that is right up against the curve, but only touches the curve at this one point. So this is the tangent line. Now the key is the slope of the curve at x equals the slope of the tangent line. How about, all right, the tangent line that goes through x. So at this point, the slope of this curve at that point is the same as the slope of the tangent line. So what we really do when we want to find the slope of a point on a curve, we don't necessarily, we really need to find the slope of the tangent line. Because what happens if you try and pick 2 points, say you wanted to find the slope down here. So here's your tangent line down here. Looks about like this. Well, you know, if I want to find the slope here, to find the slope, you need 2 points. So what if I use this point and I choose another point on my line right here? So then I connect those 2 points, because if I use those 2 points and find the slope of that line, well, look at the slope I find here is not even the slope what I'm looking for. So I can't just choose 2 points on a curved line and find the slope and have that be the slope at this point. Instead, I have to actually find the slope of the tangent line. So that's what we're going to do. Now let me tell you, here's another definition we're going to go to in a minute. Whenever you do what I just did here, whenever you pick 2 points on a curve and then you draw a straight line through those 2 points, that line has a special name. We call it a secant line. And in a minute, you're going to hear me use this word again. So a line that touches the curve at just 1 point and comes up right next to the curve, we call it a tangent line. If we actually just pick 2 points on the curve and draw a line through that, it's a secant line. So for example, if I had a parabola here, I could choose 2 points here, and if I draw a line, that's called a secant line. That's sort of an extreme example. But anytime you have 2 points on a line, the line that goes through the 2 points is called a secant line. All right. That was all sort of preparation to get ready to show you what I want to show you, which hopefully you will understand now. So in summary, we're trying to find the slope of the tangent line next to a curve. Because when we know the slope of the tangent line, that's going to be the slope of the curve at that point. And that's what we really want. We really want the slope of the curve at that point, but the way we're going to get there is to find the slope of the tangent line. So here's what we're going to do. I've already sort of made a graph. So let me draw what we're going to do here now, and as we talk about it, you'll be able to see how we come up with the equation to find the slope of the tangent line. So this is like a parabola. I drew this side up here. I didn't finish it over here. And I'm going to use a pen so I can write very precisely. Hopefully you can see this. Here's the point at which I want to find the slope of the tangent line. Even though there are numbers here, for what I'm showing you now, we're not going to even work with the numbers. It's just all going to be symbols. So let me go ahead. I'll even draw it in red. Maybe you can see, I don't know if it will look red on your screen or not. I'm going to draw the tangent line at this point in red. So what I really want, I want the slope of the curve at this point. Normally, when we find the slope, we take 2 points and do rise over run. But I can't do 2 points on this curve because when I choose my second point, it's not really going to be the slope at this point. So what we do is we go ahead and draw a tangent line, because the tangent line at this point will in fact be the same So what I really want to know is, what is the slope of this tangent line? I'll even label it. Yeah, you can see that it's red. So here's my tangent line. So I want to find the slope of this point on the curve. The way I'm going to do it is I'm going to draw the tangent line, because the slope of this tangent line is the same as the slope of the curve at that point. So now the question is, okay, let's try and find the slope of that tangent line. But the tricky thing is, the only thing we know, the only thing we can sort of use are points on the curve. I can't just randomly choose 2 points on this tangent line, because I don't really know anything about this tangent line. All I can do is choose 2 points on this curve. So here's what happens. Let's say, as a first guess, I'm going to choose this point, and I'm going to choose maybe this point right here, and I'm going to connect those 2 points. That's called a secant line. We just talked about that. When you have 2 points on a curve and you connect them, it's called a secant line. So this is sort of in purple. I don't know if the purple and the red look different. Looks maybe a little different. This is called a secant line. Now the reason I draw a secant line is because since I can only have 2 points on my curve, I say, well, let's go and draw a secant line and see if it's sort of kind of close to my tangent line. Now, to be honest, this one's not too great, because look at my tangent line, and I'm trying to find a slope. So it's a slope like this. Think of the steepness. But my secant line, which has 1 point down here, but the other point up here, it's not too close. But what I want to do is, even though this is not a great estimate, I want to go ahead and calculate the slope of the secant line. Even though it's not going to be quite right, let's just go through how to calculate the slope of the secant line. Now that's not too hard, because we know when we have 2 points on a line, we can calculate the slope. But the key is, I'll mark it right here, this the y-axis, what I call the y-axis, we want this to be sort of function notation. So the horizontal axis is x, the vertical axis is f of x. And this is why a few minutes ago, I sort of showed you how if we have a graph in function notation, we can still do the slope. And that's what I'm going to do here. Except I'm going to do something a little bit different. Normally, if we call this point 1 and point 2, we have x1, y1, x2, y2. That is something a little bit different. I'm going to call this point x and f of x, right? So like xy, but instead of y, but f of x. So really, I'm going to call this down here, right here, I'm going to call x. I'm sort of using x twice, but this is x. And this right here is going to be f of x, right? So like this point here is x, f of x. Here's what I'm going to do. Up here, instead of doing like x2, y2, what I'm going to do is I'm going to actually say, from this point to this point, how far do I move horizontally? Horizontally, I move that far. I'm going to call that distance h. This is almost like the run, in rise over run. What's the change in the horizontal? What's the change in the left and the right? It's this distance h. Therefore, this point up here, what would the x value be? It's going to be x plus h. In other words, this point right here is x plus h. Because if x is this distance, I add h, this is x plus h. So for this point, I shouldn't put this here, it's x plus h is the value of x. Now the value of y, or in this case, function notation, let me go back here. What did I do here? Whenever you have a point in function notation, if this is my x, x2, in function notation, it's just f of x2. So whatever's here goes here. Down here, when you have x1, whatever's here goes here. Look at this point. My x is actually x plus y. So what is this value going to be? F of x, x plus h. F of x plus h. So this is why I said the notation can get a little confusing. So let's review it again. I'm choosing a point here, and I'm calling this point x, y, but I'm not going to use y. I'm going to use function notation. So x and f of x. My second point, what I decided to do for my value of x, I just looked at how far did I move to the right, and in this case, I moved the distance h. So therefore, my value of x is x plus h. And then the y value in the function notation is always f of whatever my x is. So this is f of x plus h. So now the big question is, now that I've got these 2 points, let's calculate the slope. Let me try and do it right here. Maybe I do it. I'll do it up here. So the slope is y of my second point, f of x plus h, minus y of my first point. In this case, the y is f of x. y2 minus y1, the change in the y's over the change in the x's. And if I think of like x2, my x of my second point, it's x plus h minus x of my first point, which is x. So this is the traditional way you calculate slope, like y2 minus y1 over x2 minus x1. The change in the y's, the change in the vertical, the change in the up and down over the change in x, or the change left or right. But what's interesting is this can be simplified, because look at the denominator. I have x plus h minus x. Look at these x's cancel out. So I'm going to, with my blue marker, to make it very clear, right? The slope ends up being f of x plus h minus f of x all over h. Now this might look familiar to you because in this class, they've had you do some function problems. And what did they call this? They called that the difference quotient. Of course, you didn't know it at the time, but they were sort of preparing you for this step. That's why they had you do some problems where they had you calculate the difference quotient, because we were going to need to use it again at this point. So let's take a step back. What have we done? We took this graph. Our initial goal way back then was to find the slope of the curve at this point, and I drew my tangent line. But the only way I can try and sort of kind of figure out the slope of the tangent line is maybe to pick 2 points on the curve and draw my secant line, and then find the slope of the secant line and just hope that the slope of the secant line is pretty close to the slope of the tangent line. And in this case, it's not very close actually, but despite that, we went ahead, we defined our 2 points, we went ahead and calculated the slope, and we get this difference quotient. All right, so that's a big part of where we're headed. That's step one. So in a sense, this difference quotient, sometimes we call this the slope of a secant line. Because we had 2 points here, this is called a secant line. It's not really the slope of the tangent line. It's sort of, I don't know, you can look. It's the same direction, but not really the same. However, there's one thing we can do. There's one thing we can do to make the slope of our secant line look more like the slope of our tangent line. And you know what we can do? We can try and move our second point closer to our first point. In other words, just for fun, let's go, instead of having my second point be here, how about if my second point was down here, or my second point is actually pretty close to my first point. So now, if I draw my secant line of those 2 points, now if we compare, so here's our goal to find the slope of the tangent line. Our first attempt was these 2 points. That line was not so great. But you know what? As I moved my second point closer to my point, if you look at this line, this new secant line is definitely closer to this line than the first one. And the principle is, we can't really show it here, but you know what you can do? If you keep taking that second point, and as you keep moving it closer and closer to the first point, you know what happens? As that second point is closer and closer to the first point, then the secant line begins to look almost like the tangent line. You can imagine in your mind, if you put a point almost, the second point almost right next to the first point, and then you drew the line, it would almost look just like the tangent line. So the key idea is, as you move the second point closer and closer to my original point, the secant line looks almost like the tangent line. So actually that's important enough. I'm actually going to write it down as I say it again. So here's the idea. Okay, let me show you one thing before I write it down, because what's going on? When I keep saying we move the second point closer and closer to the first point, you know what I'm also saying? Remember this distance h? This is the distance between my point and my second point. As my second point gets closer and closer to my original point, what does h do? H gets smaller and smaller. In other words, for this point here, my h would have been this distance. And you can imagine, as my second point gets really close to my original point, h gets really, really small. So the idea is, when that second point gets close to my original point, this distance h gets really, really small. All right, so now having said that, let me now go sort of restate some of these key ideas, and we'll look at that graph again in a minute. So I would like to say the goal is to find a secant line that looks like the tangent line. And the reason we do that is because that means the slope of the tangent line, which is what we're trying to figure out, would equal the slope of the secant line, right? If you have two lines that are almost identical, that means the slopes are the same. So this is another way of saying, hey, I found that my secant line that almost has the same slope as my tangent line. How do we make this happen? Here's what I just said a minute ago. Let me state it and then we'll talk about it. As h, remember h is the distance, the sort of like the run distance, the x distance between the 2 points. So as the second point gets closer, that h gets smaller. As h gets smaller and smaller, the secant line, I'll use this word, approaches the secant line approaches the tangent line, right? When I say as h gets smaller and smaller, it's another way of saying as the 2 points get closer and closer together, that secant line between the 2 points approaches or begins to look just like the tangent line. Now, one last principle to top this all off. What does this mean as h gets smaller and smaller? You know what we could say? We could word this differently. I could have said as h approaches 0, right? That's what it means for h to get smaller and smaller. We can say, hey, as h approaches 0. Well, you know what? This wording here, we've actually used that wording before just a little bit ago. And that was when we talked about limits. Remember, we talked about limits as x approaches a number. Well, in this case, what I want to do is I want to look at the limit as h approaches 0. This is what I want to happen, because my goal is, to accomplish my big goal is, I want my original point and my second point to be as close as possible. For those 2 points to be as close as possible, I want h to be as small as possible. What I really want is h to be really, 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 really close to 0. And the reason why we call it a limit, because h can never equal 0. Because if h ever equals 0, then the 2 points are on top of each other. And then you cannot do your slope calculation. So the 2 points have to be separated, but I want them separated by as small as amount as possible. Matter of fact, I want the x, sort of the horizontal, sort of the run distance between those 2 points to almost be 0. So this is really what we're trying to make happen. So now, to finish this off, here's what we do. We say, we wrote up here, we figured out the equation for the slope of the tangent line. So what I really want is, I want to find the slope of the tangent line when this h, when h is as small as possible. So I could say what I want I want to know what the slope is when h approaches 0. I'll call this the slope of the secant line. I want to know the slope of the secant line when h is almost 0, when the 2 points are almost right next to each other. But of course, the slope of the secant line, we worked up an equation from the other page, and it was f of x plus h minus f of x over h, the difference quotient. So once again, we're almost done. This is the big reveal. I'm trying to find the slope of the secant line. So the secant line connects 2 points, but I want those 2 points to be as close as possible. So I say the limit as h, the distance between those 2 points, the x distance as small as possible. But we already worked up sort of an equation for the slope of the secant line. The slope of the line that connects those 2 points was this. So I can now say the limit as h approaches 0 of this is what I really want to find. Because you know what this is going to be equal to as h gets to 0? It's basically going to be equal to the slope of the tangent line. Right? Because as the 2 points get really close together, the tangent line and the secant line almost become like the same line. That's what we're doing. So the slope of the tangent line, we give another name in math, and basically we call it the derivative. So there's the big word in calculus, the derivative. The derivative, from now on, you're just going to hear me call it slope. The derivative is the slope. Bottom line is, you have a curved line. I want to find the slope at this point. You know what I do? I go find the derivative at that point, and that's a slope at that point. Because the derivative is like the slope of the tangent line, which is the slope of the curve at that point. That's really the key takeaway. The derivative is another word for slope. So therefore, there's 2 different ways they like to write derivative. One way, if they use function notation, they write f of x, but you put like a little tick mark up here. So this says the derivative of f of x. So f of x is like your function, it's your curve. But there's a second way. So this sort of is when you're using function notation. So you know f of x equals x squared plus 2. You're given some function, and if you want to find the derivative, it's written like this. But there's a second way you're going to see all the time, and the derivative, and we call this dy, like the letter, dy over dx. A lot of times you just say it dy dx. And a lot of times we use that if we're given our function like an equation. So there'll be some problems, once again, instead of f of x, they use y, which You know by now f of x and y are swapped back and forth all the time. If you're given an equation like this, y equals x squared plus 2, and they say to find the derivative, then a lot of times they write like this, dy dx, because you have a y and an x here. Once again, these are identical. The derivative and derivative. So therefore, let me just write it in function notation. The big equation to calculate the derivative. It's this right here. The limit as h approaches 0 of f of x plus h minus f of x over h. So here's the big final step. So let me summarize what we were doing. Way back at the beginning, I said this is all about finding the slope of a tangent line. You've got a curve. I want to find the slope of the curve at a point. The only way I can do that is to draw a tangent line and try and find the slope of the tangent line, because that'll be the same as the slope on my curve. Then we decided, well, how can we do that? So we went through all this work. I mean, this graph, it's pretty involved. Learning about the secant line, you got 2 points, you try and get the points. All that stuff, you can look it over again. And all the math and all the definitions. And you finally get to the point where you say, I could also call this the slope. The derivative is the same as the slope. The slope of the tangent line, which is the same as the slope of the curve, ends up being this sort of ugly looking expression. The limit as h approaches 0 of f of x plus h minus f of x over h. This is almost like the formula you have to use. If you're given a function, you're given an equation, and you're asked to calculate the derivative of that function, this is what you have to do. So this is why you have to know how to use function notation, but then you also have to know how to apply limits. And that's why we had to learn about limits and how to calculate limits. Because when we're going to calculate these derivatives, we have to apply this formula, this equation. So I'm going to stop now. In the next video, we're going to actually take some functions and we're going to use this definition to calculate the derivative of those functions. And once again, why are we calculating the derivative of a function? Because a derivative is the slope. It may not be quite so clear, but when we do a few problems in the next video, then you'll see how this all sort of fits together. All right, so let me stop now, and then we will start calculating some derivatives using this definition.